What's the coolest job you can imagine? For some people, it might be the sort of work that stimulates the mind like nothing else. Brain surgery, engineering, high-octane laws. But others might pick their dream job for the vibes, teaching surf lessons, spending the summer in a fire tower, or leading meditative retreats in the countryside. Some might dream of getting paid to watch movies as a critic. For our part, here at S3Abbies, we think the whole YouTube thing is pretty cool too. But in all the world, it's hard to imagine a job more awesome than building super advanced equipment, strapping it to a bunch of rockets, and blasting it into space to explore our universe. And if you do want to do that job, there's one place to go, and that would be JPL, the Jet Propulsion Laboratory. And it's responsible for everything from America's first satellite to the Voyager probes to the first rover on Mars to a series of future spacecraft that will explore interstellar space and explore the extraterrestrial oceans in our own solar system. It is a hotbed of innovation, a magnetically attractive destination for some of the world's best minds, and a global leader for space exploration in our solar system and beyond. This is JPL, the place where the magic happens. The story of the modern JPL traces all the way back to 1936, when a group of graduate students from the California Institute of Technology, better known as Caltech, banded together under the direction of a Hungarian scientist named Theodor von Karman. At the time Caltech began working on rocket technology, it was the only university-based research center in America to be doing so, a title it would keep until 1940. And the ones doing the work were the so-called Suicide Squad: Frank Molina, Jian Huisen, Weld Arnold, Apollo Smith, Jack Parsons, and Edward Foreman. The group had initially banded together in support of Frank Molina's graduate thesis, which was intended to explore the then-emerging science of rocket propulsion. Molina had long been fascinated with spaceflight after having read Jules Verne's From the Earth to the Moon as a 12-year-old boy, and he'd brought his buddies Parsons and Foreman along for the ride after he'd gotten into Caltech. Neither Parsons nor Foreman were students themselves, but they were both promising self-taught chemists who wanted to be doing the same sort of work that Molina was, and they were more than happy to come along for the ride. As Molina's work was approved and then began to take shape, so too did the rest of the Suicide Squad, who got their name due to the explosive, cutting-edge, and often rather dangerous work that they were doing. In fact, those complaints eventually got forceful enough that the squad was gently banished from their Caltech lab, eventually finding a testbed in Arroyo Seco Canyon just outside of the city of Pasadena. Using both solid and liquid fuel propulsion systems, the Suicide Squad experimented with rocket propulsion for several years, churning out a study on the characteristics of a rocket motor and drawing attention from General Hap Arnold, Chief of the Army Air Corps, who wanted the group to experiment with using their jets to help heavily laden warplanes take off with, say, a bomb load that they would later drop in flight. It was this critical demand that gave the Suicide Squad their start. They got a lucrative new contract, and they got a name: the Guggenheim Aeronautical Laboratory. By the summer of 1941, the team had done several test flights strapping their rockets to a monoplane and successfully getting it into the sky. Not long after, they discovered combinations of fuel that ignited spontaneously when they came into contact with one another, thus completely eliminating the need for ignition systems and creating the first storable rocket propellant. Within a few years, the Suicide Squad set themselves up as a business called Aerojet, which would become only the second rocket company in American history. With a new headquarters in Pasadena, Aerojet sold off thousands of rockets to both the military and civilian customers. But beyond just their commercial enterprise, the Suicide Squad remains a highly influential research group, with their academic arm consolidating under the Jet Propulsion Laboratory name in 1943. During this time, the JPL developed two ballistic missile systems, the MGM-5 and the MGM-29, better known as the Corporal and the Sergeant, as well as a range of other weapon systems that would eventually give rise to modern rockets, missiles, and other munitions. They also led the way in developing duplicate rockets to better understand Nazi Germany's V-2 rocket program. But after the war's end, the JPL started eyeing the prospect of a transition out of simple weapons design research and into a far more grandiose endeavor: space exploration. By the time the United States and the Soviet Union eventually settled into their Cold War posture, the JPL had already figured out many of the fundamental technologies that they would need in order to start grafting together a spaceflight program, including even a cutting-edge supersonic wind tunnel, so when the time came for JPL's attempt to get in on the budding American space program, they had everything they needed to make a compelling case. Although their first-choice proposal to work with Werner von Braun's team to put a satellite into Earth's orbit was declined, they were instead set to work on exploratory technologies that would bring nuclear warheads back to sea level after reaching the edge of space. Over the course of several missions, the JPL proved that a warhead could make a suborbital flight and not burn up on re-entry, basically clearing the way for intercontinental ballistic missiles. But it wouldn't be long until JPL got the golden goose that they had really been after. Following the US Navy's unsuccessful and rather embarrassing attempt to launch a satellite into orbit, the Army Ballistic Missile Agency and JPL were allowed to team up and try to right that wrong. What they made was known as Explorer 1, a thin, missile-shaped satellite that could be launched into orbit on a rocket and sent to orbit the Earth. Not only was it a statement that the US could do the same thing as the Soviets following their launch of the Sputnik satellite, but it also went a step further, carrying a cosmic ray detector on board that would allow it to perform real scientific experiments. The detector would ultimately support the theories of Dr. James Van Allen of the University of Iowa that the Earth is protected by radiation belts that shield it from otherwise lethal cosmic rays. The JPL designed, built, and put Explorer 1 into orbit in the span of less than 3 months, launching it on January 31st, 1958. It would transmit for the following 4 months, orbiting the Earth once every 114 minutes, or 12.5 times a day. It would keep that orbit until March 31st, 1970, eventually burning up in the atmosphere after 58,000 orbits, but by then it had already long since completed its work. And for the engineers and scientists on the ground who had built it, Explorer 1 had been like hitting the jackpot. The JPL had been in just the right place at just the right time to come through for what the United States needed, and they ensured that they'd be leading the charge for everything that came next. NASA began its operations in October 1958 with the express mission to take humanity to the stars and win the space race for America. 2 months after NASA opened its doors, the JPL was transformed from Army oversight to the NASA umbrella, bringing expertise in a whole lot of areas that NASA badly needed. JPL were already leaders in rocket propulsion, guidance and control, space telecommunications and technology testing, and their team immediately moved to the leading edge of NASA's ongoing projects. Then, as now, JPL was placed under the Caltech banner, occupying a site of about 168 acres near the place where the Suicide Squad first tested their early rockets. And then, as now, they were NASA's only federally funded research and development partner, giving them a level of closeness to the organization that no other outside research center has ever come close to touching. The first of JPL's major programs at this time was the Ranger project, an attempt to launch probes at Earth's moon in order to photograph and survey its surface. The plan was fairly straightforward. Build a probe that could take pictures and then relay them back to Earth, shoot it at the moon as precisely as possible, and have the probe take as many pictures as it can before smashing into the lunar surface. Far from an arbitrary decision to litter the moon with junk, it was the best mechanism that NASA had at the time to get close-up pictures, with some high-resolution images from the later probes coming from as close as just 300 meters from impact. Unfortunately, the Ranger probes suffered through a number of difficult early moments before they found their footing. Rangers 1 and 2 were unable to depart Earth's atmosphere due to the repeated failure of the rocket engines that were supposed to launch them into space. Although Ranger 3 was able to get to space, it was off course and ended up missing the moon completely. Ranger 4 got out of the atmosphere and was correctly aimed at the moon, but it was disabled completely during the launch and was not able to take any pictures before it impacted. Ranger 5 was also disabled when it got into orbit, and it ended up missing the moon too, and even though Ranger 6 had a perfect launch, a perfect flight, and a perfect impact, it was unable to take any in-flight pictures due to an accident. But whatever JPL and NASA might have been at the time, we can't say they weren't persistent, because when Ranger 6 became the latest of JPL's failures, they tried again with Ranger 7. This time, featuring a redesigned television system, the probe executed its mission perfectly, sending 4,300 pictures of the moon on its approach before crashing as expected. Ranger 8 would do even better, taking 7,300 images of the very site where Apollo 11's astronauts would touch down just a few years later. And wrapping up the Ranger project, Ranger 9 smashed into the moon a month after its immediate predecessor, providing 5,800 images in the process. Around the same time as the Ranger series, the JPL was also working on the Mariner program, a line of 10 Explorer probes that aimed to reach and study the planets of Mercury, Venus, and Mars. These probes carried a whole suite of scientific instruments, from cameras to devices to measure magnetic fields and particle flow to microwave radiometers. Arrayed into a hexagonal or octagonal fuselage, the Mariner probes each featured solar panels and a dish antenna, as well as a system to stabilize them on all 3 axes of motion and ensure that they wouldn't spin during flight. Mariner 1, unfortunately, wasn't much to write home about. Although it lifted off successfully in July of 1962, it had to be destroyed about 5 minutes later due to a rocket rocket malfunction. Mariner 2, though, had no such issues. It blasted out of Earth's atmosphere about a month later and successfully completed a 3.5-month-long voyage to the planet Venus. While in transit, it confirmed the presence of solar wind in space and measured the phenomenon. It measured interplanetary dust and found that the dust occurred at a much lower rate than previously believed, and it picked up the effects of multiple solar flares emanating from our sun, as well as various other cosmic rays that originated outside our solar system. When it arrived on Venus, it revealed a planet with cool clouds sitting high in the atmosphere, but with extreme heat at or near the planet's surface. After it completed its mission, it entered an orbit around the sun, where it remains to this day. Next up were Mariner 3 and 4, both intended to fly by Mars and give humanity its first close-range look at the planet. Like the prior pair of Mariner craft, the first attempt was a dud, but the second was a resounding success. On July 14th, 1965, Mariner 4 snapped the first pictures ever of the Martian surface, revealing a wide range of impact craters and signs of frost. After its flyby, Mariner 4 ended up staying active for several years past its anticipated date of systems failure, and JPL and NASA used the opportunity to coordinate with Mariner 5 in order to provide more accurate measurements on solar wind and cosmic environments. And speaking of Mariner 5, the craft's mission was to probe Venus's atmosphere, providing information about its temperature and atmospheric pressure before it eventually lost contact with Earth. Mariner 6 and Mariner 7 were teammates on another Mars mission, one that went smoothly now that JPL had plenty of experience launching probes. In these flyovers done around Mars's equator and its southern hemisphere, the probes captured and relayed hundreds of photographs while analyzing the planet's atmosphere and surface. Mariners 8 and 9 seized on that success with the hope of entering orbit around Mars to conduct a longer mission. While Mariner 8 was lost in a rocket failure, Mariner 9 eventually became humanity's most valuable Martian probe yet. The probe formed a mosaic-style portrait of the Martian surface, as well as close-up pictures of its two small moons settling into orbit around the red planet and working a while before it was eventually shut off. NASA's best guess is that it has crashed into the planet by now, deteriorating in orbit, although it could be, hypothetically, still up there. And lastly, there was Mariner 10, which became the first spacecraft ever to use the so-called gravity assist trajectory in its travels. The maneuver required Mariner 10 to put itself nearby Venus in order to enter its gravitational well, but enter at a precise trajectory that would allow it to slingshot off in the direction of Mercury. Not only did this make Mariner 10 the first spacecraft to try and succeed with such a maneuver, but it also made the craft humanity's first to encounter two planets other than Earth. Because of the precision of its gravity assist, it was able to pass over Mercury multiple times, taking and returning the only pictures of the planet that people would receive until the 2000s. Finally, this era in JPL's history was also known for the Surveyor program, a series of robotic spacecraft that were sent to the moon in advance of the Apollo program. Surveyor had a few basic goals: to prove that spacecraft could perform soft landings on the moon, to show how spacecraft could make corrections to their course mid-flight, and to evaluate the lunar soil for its suitability for landing, as well as its chemical composition. At this time in the space race, the world just didn't have any way of knowing how thick the moon's layer of dust was, and had to accept the possibility that it could, hypothetically, go down for multiple feet or even multiple meters in an unstable, loose-packed surface that would make human exploration impossible. All of the 7 Surveyor missions all made it out of Earth's atmosphere, and 5 landed safely on the lunar surface. The other 2 did crash, but at least they crashed on the moon rather than being unable to hit the thing entirely. Surveyor 6 even lifted off from the lunar surface in order to prove that such a takeoff could be done, and all the probes sent back data and proof of concept validation that would pave the way for the Apollo mission's success. By the mid-1970s, JPL's mission was shifting somewhat. They'd already set off NASA's golden age of space exploration, they'd already proven themselves as the go-to source for all things extraterrestrial, and they'd already adopted the practices that would become the way of the future, emphasizing cutting-edge but fundamentally utilitarian design, employing not just men, but women as mathematicians and engineers, and producing the sort of results that had put the Americans ahead of the Soviets in the space race. But with Mercury, Venus, Mars, and the moon basically done and dusted, it came time for JPL to turn around. Moving forwards, their missions wouldn't be bringing spacecraft closer to the sun or visiting a next-door neighbor. Instead, they'd be going out, way out, into deep space. In 1965, mathematicians revealed that a rare instance of planetary alignment between Jupiter, Saturn, Uranus, and Neptune would make it possible for a brief window in the late 1970s for a probe to visit all 4 planets by using the same gravitational slingshotting method that JPL had already pioneered. Naturally, JPL were the first choices to work on the program, which began under the name Mariner Jupiter Saturn 1977, but was quickly changed to the much more catchy name Voyager. The plan was to launch 2 Voyager probes in total. Voyager 2, which would be launched into orbit first, and was named 2 because it would reach Jupiter and Saturn second, and Voyager 1. The reason for the discrepancy was a matter of targeting. Voyager 1 was just going to visit Jupiter and Saturn with a flyby of Saturn's moon Titan, but Voyager 2 was going to visit all 4 of our solar system's gas planets, meaning that it needed to come in at Jupiter from a different trajectory in order to get its slingshots just right. The probes would launch 16 days apart, both taking off successfully, and after takeoff, Voyager 1 notched another global first for the JPL's belt. The world's first true group selfie. It was shot by Voyager 1 as it looked back on planet Earth. A bit over a year and a half after it left Earth's orbit, Voyager 1 made its approach on Jupiter, photographing not just the planet, but its rings and several of its moons. Voyager 1 snapped pictures of active volcanoes on the moon of Io, the grooved terrain of the surface of the planet Ganymede, the lighting on Jupiter's surface, and the true nature of the planet's Great Red Spot, an incredibly large storm that in some ways is reminiscent of cyclones back on Earth. A little over a year later, helped by Jupiter's gravitational effects, Voyager 1 reached the planet of Saturn, discovering 3 moons and proving that they are a necessary sort of gravitation or shepherd that keeps the planet's magnificent rings in order. The probe got a closer look at the ring system itself, plus some beautiful views of the moon Enceladus, while gathering data around the moon Titan that showed it to have a nitrogen-rich atmosphere. This was the last celestial body on Voyager 1's travel itinerary, but certainly not the end of its mission. In the intervening years, it captured a series of pictures called the Solar System Family Portrait, imaging Venus, Earth, Jupiter, Saturn, Uranus, and Neptune as tiny dots. After that, the probe passed into interstellar space and continued sending readings back to Earth. As of now, it's located over 24 billion kilometers from the Earth, and it's expected to be able to continue operating its instruments until around 2025. And then there's the journey taken by Voyager 2, which made it to Jupiter a couple of months after its sister craft. During its time there, Voyager imaged the planet's rings for the first time, discovered another moon, and provided close-up shots of the ice moon of Europa. It also confirmed that several eruptions observed on Io by Voyager 1 were still ongoing. When it arrived at Saturn, Voyager 2 photographed several more icy moons, including images of the moon Enceladus that indicated possible geological activity below its surface. From there, it traveled to Uranus, identifying a total of 11 moons and discovering that the planet's magnetic field is uniquely tilted. It identified another ring system and revealed Uranus as exceptional cold before course correcting and flying toward Neptune. Upon arrival at our 8th celestial neighbor, the probe identified 6 more moons, yet another ring system, and a massive storm similar to Jupiter's Great Red Spot before traveling onto the moon of Triton and observing its great geysers. Like Voyager 1, Voyager 2 has since passed into interstellar space, and like Voyager 1, it carries one non-instrument piece of payload, a gold-plated audio-visual disc that could conceivably be found and read by intelligent life outside our solar system. If those discs are found, it'll likely be hundreds of thousands or even millions of years into the Voyager mission, presumably putting yet another historic achievement into the annals of the JPL. Of course, there's a fairly low probability that the JPL will be around to see that future come true. Also of note during this time is the Galileo mission, a deep space operation that placed an atmospheric entry probe in the immediate vicinity of the planet Jupiter and let the probe travel inward toward the planet, transmitting data while held back by a parachute before it was eventually lost. The mission began when the probe was dropped off into Earth's orbit by the space shuttle Atlantis, and then made to conduct flybys of Venus and Earth to get more of those gravity assists that we discussed earlier. During those transits, the probe took pictures and readings, also capturing close-up pictures of asteroids as it passed repeatedly through the asteroid belt. It was able to observe the collision between Jupiter and the comet Shoemaker-Levy 9, and when it eventually released its atmospheric probe, the probe was able to provide detailed readings for nearly an hour before it was swallowed up by the planet. Galileo itself settled into orbit around Jupiter for another several years, encountering its 4 largest moons to take close-up portraits while capturing images of Jupiter's auroras and storms. Eventually, the craft completed its mission after closely imaging the volcanic moon of Io. It ended its life with a graceful fall into Jupiter's atmosphere, where it joined the probe that launched all those years ago. Now, what we've discussed so far from the JPL is already a hell of a legacy, but even after having mapped out every planet in the solar system and charted a course to interstellar space, the good folks at JPL still weren't satisfied. Next up, was a foray into robotics, expanding on the technological and data innovations that JPL had already pioneered over the past few decades. JPL had already set 2 orbiters around Mars, the Viking probes, and each had replicated the work that JPL had done on the Moon and elsewhere, photographing the surface and putting down landers in order to analyze potential landing sites for later probes. By the 1990s, humanity had set its sights on returning to Mars and conducting more detailed explorations of the planet's surface, something that rovers would be absolutely essential to, and it was JPL that was going to take the lead. First up was the Pathfinder, a technology demonstrator spacecraft that was supposed to deliver a landing craft to the Martian surface, fully equipped with instruments, and then release a robotic rover to conduct further exploration. JPL's rover, named Sojourner, would be the first robotic rover ever sent to another planet, and the instruments it carried would provide analysis of the Martian atmosphere, its geology, and its climate, in order to broaden our understanding of what existence on the red planet was really like. It was also a foray into so-called faster, better, cheaper principles of spacecraft construction, which were, well, they're exactly what they sound like. The Pathfinder lander cost just $150 million to design, and the rover itself was just $25 million, with an overall mission expenditure that was just 1/15 cost adjusted of what the Viking missions had cost. Sojourner and its lander conducted a wide variety of studies at their landing zone, as well as setting up the architecture for a basic meteorological station and sending color images of the rover's exploration of the planetary surface. The lander's descent was also innovative, coming down via a capsule first, then a supersonic parachute, then a rocket boost to slow down the descent, and then finally a series of airbags that allowed the lander to bounce at least 15 times before eventually settling. Next up were the 2 Mars exploration rovers, Spirit and Opportunity, which each touched down on the Martian surface in January 2004. Spirit and Opportunity were designed and built with the intention to search for evidence of past water activity on the Martian surface, searching for and analyzing a range of potential rock and soil types that might have held clues to a possible wetter past. They also searched for evidence of volcanism, erosion, hydrothermal activity, and the presence of water, as well as small cues that might have indicated what Mars would have looked like when water was present. The ultimate question at the heart of the mission was whether Mars might have ever had the conditions for life. The missions were only scheduled to last a total of 90 Earth days, but both rovers proved capable of enjoying a far longer lifespan. Spirit explored the Martian surface from 2004 to 2010, while Opportunity was able to hold out until 2018. In that time, the rovers found concrete evidence of liquid water on the Martian surface, specifically a salty sea that had since evaporated. They also identified rocks that mimicked volcanic basalt and learned that all dust on Mars is most likely magnetic, containing small amounts of chemically bound water inside the dust itself. By the time both rovers ended their service lives, they had made invaluable contributions to our understanding of Mars's history, as well as its potential ability, or lack thereof, to host spacefaring humans one day. Next in line was the Curiosity rover, which touched down on Mars inside Gale Crater in August of 2012 and has since conducted a full investigation of Mars's climate and geology. Curiosity uses newer, better tools and designed to do basically the same work as the Spirit and Opportunity rovers, looking for indicators that its landing site had ever offered an environment that could have hosted microbial life. But in Curiosity's case, it can do much higher-level analysis of carbon components, other chemical building blocks for life, and a range of factors relating to the past and present of the Martian surface. The Curiosity rover has captured global imagination even more effectively than the rovers that preceded it, and it's got the most personality by far of anything currently living on Mars. Just by example, it played itself a rendition of Happy Birthday after it concluded its first year on Mars, although NASA apparently didn't feel that this adorable ritual was worth repeating in the subsequent years. Curiosity apparently can only have sad birthdays now on, so thanks a lot, NASA. Admittedly, more important than its birthday song are the discoveries the Curiosity has made while on Mars. For example, it's found stretches of land that are believed to have been a stream bed, and other lands that might have spent over 1 million years under the surface of a series of lakes. It's confirmed that Mars has all the right chemical traces and indicators to suggest that it might once have supported life, and even water that humans might consider drinkable. It's identified organic compounds inside of Mars rocks, indicating that all the requisite building blocks for life have been present there at some point, and it's even tracked an increase in methane, a compound produced by living organisms and chemical reactions with liquid water during the time that it's been present. Put simply, the JPL's rover did just about everything humanity could do to piece together the high likelihood of past life on Mars short of shaking a Martian's hand. Then there's the Perseverance rover, which JPL manufactured and kindly allowed NASA to shoot into space in July of 2020. When it arrived about 8 months later, Perseverance joined Curiosity in searching for markers and evidence of former microbial life, as well as laying the groundwork for future manned missions to Mars. The rover comes with some moderate upgrades over Curiosity, as well as one other JPL invention. This is Ingenuity, an autonomous mini-helicopter sidekick that's capable of flying up to 60 feet high in the thin Martian atmosphere, pushing 15 miles an hour if it's really feeling itself. Ingenuity's job is to prove the utility of an aerial scout on the planet, scoping out potential routes and areas of interest for Perseverance, and showing how such aircraft could be incredibly useful in a future manned mission, even if they were autonomous rather than piloted. The minicopter, like many past JPL designs, has more than exceeded the expectations with which it was designed, and it regularly runs missions providing data and scouting sites for Perseverance. JPL has also done plenty of other work in recent decades as well. In 1998, they opened up NASA's Near-Earth Object Program, which keeps watch over the solar system for large asteroids that may come across Earth's orbit. Then in 2011, they assumed operational command of a probe called Juno, built and designed by Lockheed Martin, which still orbits the planet today. Juno, which is set to complete its mission in September 2025, has worked to determine the abundance of water inside the planet, estimated its core mass, mapped its gravitational magnetic fields, and done work in exploring its atmosphere. They also managed the Cassini-Huygens mission, a joint endeavor between NASA, the European Space Agency, and the Italian Space Agency to study Saturn, its moons, and its rings. The Cassini probe itself, plus a lander on board that visited the moon of Titan, were successful beyond anything its creators had intended. Not only would it offer evidence in favor of general relativity, discover 9 new moons of Saturn, and conduct in-depth analysis of not just Titan but Enceladus, but it was able to send back incredible volumes of other data before it eventually dove into Saturn's atmosphere. NASA would earn an Emmy Award for its presentation of the Cassini mission's conclusion, and JPL would again earn global appreciation for yet another job well done. For a program that has made a habit of pushing the limits of space exploration, it should be no surprise that JPL has no outward intention of winding down anytime in the next few decades. With the world's attention shifting toward the idea of a manned mission to Mars, a return to the moon, and potential attempts to breach interstellar space and follow up on the work of the Voyager probes, JPL is just as in demand as ever, with a real possibility that its best days are going to lie ahead of it. JPL's biggest new initiative is known as OSIRIS-REx, a sample return mission that was initially drawn up in the 2010s as a way to capture material from a near-Earth asteroid and ferry it back to Earth for analysis. This is a vital step in learning how the solar system formed, how it evolved, and where organic compounds that formed the building blocks for life on Earth may have originated. The probe's already rendezvoused with its first satellite, a carbonaceous asteroid known as Bennu, and touchdown collected a sample that should be somewhere between half a kilogram and a full kilogram in weight. At the time this video was written, we're just a little over a week away from OSIRIS-REx's return to Earth, when it'll drop its payload and head back out to space. When it does, its name will become OSIRIS-APEX as it begins its follow-up mission to repeat its process with the asteroid's Apophis, which is expected to make a very close pass to the planet Earth on April 13th, 2029. When it does, OSIRIS-APEX will be right there, beginning a rendezvous that will conclude when it gets in close and studies the asteroid's subsurface. Of course, if Apophis veers off course and destroys the Earth, we'll be telling a different story, but we'll probably be fine. Don't think too much about it. But the OSIRIS craft is just one of a long list of missions on JPL's docket. Among its major upcoming initiatives is the Europa Clipper mission, set for launch in October 2024. An orbiter that will carry a whole suite of advanced instruments, the Clipper is going to perform in-depth analysis of Jupiter's moon Europa, searching for indicators that its icy conditions could host life. So too will the Psyche orbiter travel to an asteroid sharing the same name, Psyche, which is believed to be part or all nickel-iron core that once belonged to an early planet. The Euclid orbiter, which launched into space in July of 2023, is going to investigate dark matter while orbiting the Sun, and the Near-Earth Orbit Surveyor will launch in 2027, working to identify and catalogue any asteroids and comets that will eventually pass within 30 million miles of Earth's orbit. JPL is also developing a fleet of shoebox-sized four-wheeled autonomous robots that will explore Mars in a swarm, including traveling into areas that would be challenging for a bigger rover to reach and navigate, and coordinating with each other to explore and make measurements that they couldn't do alone. They're working on concepts for a future lander on Europa, which could launch as early as 2027, and they're developing components of the anticipated Nancy Grace Roman Space Telescope, an infrared telescope that will search for extrasolar planets and work to establish a chronology of the universe itself. It's a testament highlights the incredible work done at JPL that even in this video, even covering their work and achievements as best we can in a short time, there are still dozens of missions, experiments, spacecraft, initiatives, and programs that we simply couldn't cover, at least not in a piece of any reasonable length. JPL's greatest achievements are a long list of unprecedented, genuinely groundbreaking feats of space exploration, and in the day-to-day grind of their work, even the most mundane work they do adds volumes to humanity's understanding of our world and solar system. It's a place unlike any other on Earth, a place where spacefaring innovation happens at a breakneck pace, and where the end result often goes far above and beyond anything NASA asked for. It's the life's work of all the good people at JPL, and we're lucky to have them.